Yeah. So, yeah,
Okay,
please
all
go
good.
ahead.
Uh-huh.
Mhm.
So today I'll explain to you all the work that we've been doing in Oxford,
Mm,
very unashamedly focused in wearables in
mm,
very large scale studies. So I'm based in a department of population health, and I affectionately like to think of our department as the big studies department. We've got the UK Biobank study in 500,000 people. We've got the China Kadoorie Biobank study in 500,000 people. And we've got the modestly named A Million Women study, which is in 1.3 million women who were recruited about almost 30 years ago. So we study very large groups of people, try to take as many measurements in their health status as possible, and then follow them up for 10, 20, 30 years to see who develops cardiovascular disease, who develops diabetes, who develops prostate cancer, etc., and who dies. So we're looking for the essentially the drivers or risk factors for future health and disease outcomes. So the department I sit in is about 1,000 people.
mm,
And then within that, I lead a team of about 20 people who, like myself, are unhealthily obsessed with wearable sensors. So we are huge fans of wearables to try and better measure activity, sleep, circadian rhythms, heart rate and arrhythmias, etc., and how they might predict future health outcomes.
mm,
The picture to the right, just to show you, is Oxford is a place that has got a lot of history and some very different or unusual traditions. And one of those is we've got the college system. So I am vice president then of Oxford's 39th and newest college, which is called Reuben College.
mm,
And it's got a huge focus on the large challenges of this century around environmental change, medical sciences, ethics of AI, and the fundamental developments of artificial intelligence as well. So Oxford's a really exciting place and to be at right now. And over the next 40 minutes or so, I'll share with you some of the work that we've been doing in large scale biobank studies, bringing together artificial intelligence, time series machine learning of sensor data, large biobank studies, and showing you some very interesting science from that. So the first slide, and I don't think I need to tell you about this, since I know you're actively
mm,
working this with colleagues at Samsung as well,
mm,
is that there's a huge interest in wearable sensors in health nowadays because they offer this promise or allure of being able to continuously collect and passively collect non-invasively
mm,
um, information on a wide range of important health measurements, such as a person's physical activity, their heart rate and rhythms, their sleep patterns, etc. However, the impact of wearables in health has maybe been somewhat limited up to now, because what we really need is to know how do they predict future health status. And it's quite hard for a company to do that because the likes of Google or Apple or Garmin or Samsung do not have the uh, wherewithal, I would say, to track and follow people up to see what happens to their medical records 5, 10, 15, 20 years in future. It's just not part of their business models to
mm,
do that. That would be too big an R&D
mm.
effort. So I believe that bringing together public health epidemiology together then with the innovations in industry might be a really sweet spot in future. And talking about the future, in all of my slides in the bottom right, I will put in
Wow.
a reference to papers, and this is by far and away the weakest reference because it was just me having some playing around with ChatGPT. But I was just trying to figure out what is the potential market size in different areas. Because when I go to any biomedical conference, I hear nothing except about GLP-1 drugs, which are the
Mm,
weight loss drugs.
mhm,
I also hear nothing else but genomics.
mhm,
And both of those are incredibly interesting areas. There would be huge scientific advances in each of those. but the amount of people who have their genome sequenced or who need a weight loss drug is only a segment of society. Whereas for a technology such as wearables or artificial intelligence, the market size and the amount of people who would use such technologies is a much, much larger segment of society than those who will have their genome sequenced or need weight loss drugs. And I was trying to be somewhat objective to put in something that might have a larger market size than wearables. And of course, artificial intelligence uh, is a hugely transformative technology. But my argument is the intersection of wearables and AI is probably one of the most exciting spaces someone could be in right now. So if you're earlier in your career and you're thinking about an area to go into, I could think of no area that is more exciting, more productive to be in than the intersection of AI and wearables and health. And indeed, in England or United Kingdom, we have our National Health Service, who recently, back in July, produced a forward-looking report of what are the priorities over the next 10 years. And the UK National Health Service had said there will be five fundamental transformative technologies on which we have to piggyback upon. And one of those five fundamental technologies up in the top right is wearables. So there's a huge recognition in the healthcare profession that wearables can play a hugely and importantly transformative role in prevention, in treatment, and in healthcare delivery over the coming decade. So again, an incredibly exciting space to be in right now. Now, there are a few biases that I am going to bring into this talk, and I should be somewhat upfront in declaring those. The first is I love to put wearables on people rather than near people or around people. One example here is if I'm trying to capture the temperature that a person is exposed to, I really would rather the sensor is along the person rather than somewhere near them. So on the left-hand side, along with colleagues in China, we conducted a study a few years ago on about 300 individuals, and we put sensors in the community and then on the person. So you can imagine a sensor in the middle of the village just measuring the temperature, which is what all of environmental epidemiology relies on. And we can see that in the summertime on the left-hand side, the correlation between the village or outdoor sensor and the personal sensor is pretty good because people spend a lot of time outside in the summer. However, in the winter, we can see the correlation or agreement between both is really quite poor with an R squared of just zero point 0.1. Again, which makes lots of sense because in the wintertime, we don't spend so much time outside, which is where the fixed sensor is. So if I can, in any way at all, I like to have a sensor on the person's body or at least attached to their body in some way. So that's one bias that I'll bring. And then similarly, on the right-hand side, you can see we also attached PM 2.5 sensors, which capture fine particulate matter, which is believed to be important in relation to air pollution and ultimately health. But again, we can see there's a very poor correlation between the personal sensing measurement and the community sensing measurement. And in fact, this is flipped around because a lot of the air pollution, or sorry, PM 2.5 exposure happens through cooking in the home using more traditional fuels. Now, another big bias that I bring into this talk is that uh, if I can at all, I much prefer a device-based measurement to relying on a person's self-reported or perceived estimation of what they're doing. So I really don't want to, or try not to believe what people tell me. This is one example in the UK Biobank, and later I'll describe how this was derived. But in the x-axis, we've got a self-reported a sleep duration questionnaire, how long I think I sleep, and on the y-axis we got a device-based measurement. Now, this is in 66,000 people.
Mhm.
So each one of these boxes here represents a decile. So we go over to the very right-hand side, we've got a decile of 6,500 people who think they sleep 12 hours per night. Now let's go over to the left-hand side. We've got a decile of another 6,500 people who think they sleep just 3 hours per night. But if we look at the y-axis, the device thinks both these groups of people are sleeping
Mm.
maybe just about 8 hours per night.
Mhm.
So it's really hard for people to self-report and estimate or quantify time spent
Mhm.
in sleep or also in physical activity type behaviors. The correlation between device and self-reported activity is about zero point 0.2 at best. So if I can, I really want a device-based estimate rather than a self-reported estimate.
Mm.
And I think, second last bias that I bring into account is that if I can, I want to study personal health characteristics in as many people as possible. So if we look at the left-hand side, here I'm trying to look at the relationship between systolic blood pressure and ischemic heart disease. So on our x-axis, we can see yeah, blood pressure, y-axis, we see hazard ratio or risk of a stroke, ischemic heart disease. So then if we're trying to see what is the relationship within individual decades of aging, so for the 50 to 59-year-olds or the 80 to 89-year-olds, it's really hard to pick out any discernible patterns in 5,000 people. Now, we need to remember 5,000 people is about the size of the Framingham Heart Study, which has been transformational and foundational for cardiovascular care since the 1960s. And it's more or less still a lot of decisions that are made today in the cardiac clinics rely on some early information from the Framingham Heart Study, but we see it's just not large enough. However, if I go to 50,000 people or 500,000 people, I begin to get these engineering scale diagrams where I can see very clearly there's a strong association between higher levels of systolic blood pressure and ischemic heart disease across all age groups. And indeed, it's much more important for people in the older age groups because the y-axis is on a log scale.
Mm.
So large numbers provide clarity. So if I've got a wearable measurement, I want to see how it's related to health. I really want it to be in as large a data set or a large number of people as I can possibly get. And then finally, uh, what we do is probably more important than who we are. Now, this brings in to account my bias of nature versus nurture. So, how much role do our genetics play versus the lifestyle attributes that we can modify? My I do work in genetics, but the I'm a strong believer that the environment
Mm.
plays a very, very important role. So this is a paper that we recently published in Nature's Medicine Journal that was looking at the contribution above age and sex of taking into account genetic risk scores versus measurements of the environment, which might improve mortality prediction more. So you can see the polygenic risk scores maybe add 2% additional performance, whereas the exposome or environmental measurements add 17% extra um, uh, added value to the risk prediction of mortality. So again, the types of aspects that one might be able to measure from a wearable that would relate to one's environmental exposures are probably going to be much more potent and helpful than what we might get from a genetic measurement. And of course, the sharing of data and
Mm.
methods is vital for scientific progress. So anything I present today will almost certainly have an associated GitHub repository with it. And additionally, it will, any variables that we create, we return back into major resources such as the UK Biobank and China Kaduri Biobank so that other research scientists can use the derived measurements we make in new and clever ways that we could not have thought of. Because the UK Biobank study um, has 40,000 registered researchers worldwide. So, for you being a researcher in Korea, you can apply for access to the UK Biobank resource to use it in new and imaginative ways that we've not thought of. And just to very briefly discuss the UK Biobank, so it was a study of 500,000 people who were recruited about 20 years ago across 22 different centres in the UK. And they had, as I described in the very first slide, a huge amount of measurements taken on them on their personal and family history, on their physical measurements, such as their lung function and their body size. They also had give blood, urine, and saliva samples so that we could get their genetic information. And a key thing of a study such as the UK Biobank is that all the people provide consent then for future follow-up. So if I'm a biobank participant, I've given the team permission then to link up to our electronic patient record system in the UK, to our death registry system, to our cancer registry systems. So with all the biobank participants, we know when they go to hospital, what for, what other underlying conditions did they have, and when were they discharged. So it's a very, very powerful and rich resource. And the part of that that I lead is around the assessment of wearable sensors. So in 2013 to 2015, we had the aim of collecting data from 100,000 people within the biobank study. And what we gave out was a wrist-worn device called an Exivity, which was created by a small company in the UK. And essentially what it does is a very simple triaxial accelerometer. It measures acceleration forwards and backwards, side to side, up and down, and does so 100 times per second. So we get a capture rate of 100 hertz. So the data looks something a little bit like this, whereby it's time series data. So on the we got four columns essentially: time, acceleration of the x-axis, acceleration of the y-axis, acceleration of the z-axis, and the units for these axes are in gravity. Although typically we convert it to milligravity units that I'll explain a small bit later. So we're getting this very rich, dense time series information on a wide, on many, many individuals. In fact, we have, I should just very briefly show our China Kadoorie Biobank study, whereby, again, 500,000 participants, 20,000 participants of whom we give this wrist-worn device. And the China Kadoorie Biobank, unlike the UK, has got wonderful geographic variation from Harbin in the frozen north down to Haiku in the tropical south, urban-rural divide. And again, it's got measurements of genetics, family and health history, physical measurements,
Mhm.
and follow-up to know what happens to those individuals 10, 15, 20 years later via the National Health Insurance claim system. Um, so the team at Oxford, then, we've got a number of different wearables data sets. Today, I just briefly mention four of those. So we got the UK Biobank I mentioned, China Kadoorie Biobank that I've just mentioned. We've got the Charles study, the Chinese Health and Retirement Longitudinal Study, that's in a population representative sample of older adults. And additionally, we've got the ELSA, the English Longitudinal Study of Aging, that's in a population representative sample of older adults in England. So at the top, we've got the UK Biobank, China Kadoorie Biobank, huge depth and detail on people, but
Mm.
there are people who are willing to come into healthcare studies. And then below, we've got the Elsa and Charles that are kind of beautifully population representative samples across those individuals.
So,
And
Aiden, so kind of
yes, go
China
ahead.
data, can
Yeah.
you access it? Because UK Biobank is a sort of public, but China data, I
Yeah.
guess it's very closed. So are they
It
shared with the outside?
um it is possible to apply for access to the
Mm.
China Kadoorie Biobank data.
Mm.
There's a delay with the accelerometer data because even the international coordinating team here in Oxford has only just received the data about
Ah,
4 to 5 years after it's being collected.
okay.
However, there are access procedures to get access to the data from the China Cadbury Biobank, it's just a bit more difficult to get
Okay,
access than the
got it.
UK Biobank, but eventual access is possible. And indeed, if anyone is struggling with that, please do feel free to send me a message, and I'd be happy to put you in contact with a
Yeah.
relevant person at
Wow,
the China
wow.
Cadbury
Okay.
Biobank team.
Thank you.
But it's, I think, an amazing resource because too
Wow.
much of our scientific literature
Mm.
and wearables data
Yeah.
is in Western
Yeah,
settings, so we
exactly. Yeah.
desperately need
So,
some
yeah.
Asian, African, South
Yeah.
American data sets. Um, yes, we've got these different data sets.
Mm.
Some things to be really aware of is the consent rate. So we can see in the UK Biobank consent rate was 47% because we had to send out 250,000 email invites. But that was because we were sending a cold email to people about 5.5 years after they had last engaged with the study. Whereas with all the other studies, the Chinese studies and the English longitudinal study of aging, people were asked when they were having other measurements taken, are you happy to have a wearable measurement? And you can see about 80 to 90% of individuals are happy to do so. But there will be some differential rates of response. So on the right-hand side, we can see in the English longitudinal study of aging, people over the age of 80, uh, people from low education backgrounds and people from low wealth backgrounds are less likely to agree to wear a wearable device. And this is, I guess, classic across all healthcare measurement modalities. And furthermore, in the UK Biobank, as I said, we had to send out
Mm.
250,000 email invites to get our 100,000 person target sample. And what Charlie Harper and our team looked at was the group of people who were asked the question. So on the x-axis, we got years of follow-up from accelerometer wear, which essentially is years of follow-up since the question was asked. And then the y-axis is the mortality rate in both groups. And we can see the blue line is people who said, yes, I'm happy to wear the accelerometer. And the green line is people who did not respond to the question or declined. So you can see quite immediately that if you're ever asked to wear a wearable, you should definitely say yes because you will have a lower mortality rate. Now, of course, that's not the explanation. It's the types of people that agree to wear a wearable are generally a healthier bunch of people. But it's important that we take some of these biases into account.
Mm.
So now I'm going to skip forward a little bit, and I'm not going to talk about some of the basic processing that we do with the accelerometer data in terms of filtering the data using and cleaning the data and QCing the data. I'm very happy to answer questions on that afterwards. So I'm going to imagine now that we can create a measurement from the wrist Warren triaxial accelerometer data. And I'll explain a little bit later how I make the daily step count measurement, because I'll get into time series machine learning soon. But let's imagine we can make a measurement of step count. So then on the left-hand side, we've got this is analysis carried out by Evelyn Fulda then that was looking at for variations in device measured activity, how might that be associated with future cardiometabolic disease and specifically non-alcoholic fatty liver disease. So on the x-axis, we got the amount of steps that each participant is doing. We've grouped them into four categories. People with the lowest, who are in the lowest 25% of the distribution for step count, people who are in the second quarter, third quarter, fourth quarter of the distribution. And the y-axis then is a hazard ratio or risk of developing future non-alcoholic fatty liver disease. And what we can see then with the device-based evidence is, first of all, about in the second quarter, I've got a hazard ratio of 0.67. That means I've got 0.67 times the risk of being diagnosed with non-alcoholic fatty liver disease in comparison or in reference to the people who are in the lowest distribution of the step count distribution. So a 33% lower risk.
Mhm.
Excuse me. However, then we look at people in the top quarter of the distribution, they have got a 67% lower
Mhm.
risk of being diagnosed with non-alcoholic fatty liver disease
Mhm.
8 years into the future. And this is in people who are as far as we could tell, healthy when they had the wearable measurement. Now, what Evelyn also did was on the right-hand side, she looked at people's self-reported activity. Now, to be fair, the self-reported activity does show people who are more active or who think they are more active do have a lower risk. But the two big differences here are the slope of the association, so essentially the shape and the magnitude of the association. And there's very different public health interpretations to these. First of all, it is if I look at the magnitude of the association on the right-hand side, using my old self-reported evidence, I might think that people who are most active have got about a 40% lower risk.
Mhm.
Whereas when I look at the left-hand side, I can see people who are more active have got a 75% lower, or sorry, almost 70% lower risk. So first of all, I'm interpreting physical activity as being much more important than previously thought. And then secondly, if I'm trying to give a public health message, if I go to the right-hand side, it's not really clear if there's particular benefit for people who are in the second or third quarters of the distribution, or it's quite hard to tell from the shape. Whereas I go back to the left-hand side with the device-based evidence, I can see if I'm in quarter one, there's a clear benefit going to quarter two. If I'm in quarter two, there's a clear benefit going to quarter three, and so on. So there's a very nice message then that no matter how much activity you're doing, there does appear to be benefits from doing or engaging in more. So it makes public health messaging more simple and also much more informed on higher quality evidence as well. And this fits in beautifully with even that was an example of non-alcoholic fatty liver disease, but also we look uh, at mortality outcomes. Again, it's showing that the device-based evidence and the blue line is showing much, much stronger associations with the for the prediction of mortality than is the red self-reported line. Again, physical activity is probably twice as important as we had previously thought. No. And the beauty of having wearables embedded within a biobank or an existing biobank is that you don't only just look at mortality or non-alcoholic fatty liver disease, but instead you can look at your favorite disease because it's linked up to electronic patient records or electronic healthcare records. So this is an analysis taken place by Ellie Watts at the US National Cancer Institute, who looked at how is device measured activity associated with a wide range of disease outcomes. So she's looked at circulatory diseases, digestive diseases, joint disorders, etc., etc. And on the bottom, we can see if you're to the left-hand side of the line at the point estimate, that means that people who are more active have got a lower risk. Whereas if you're at the right-hand side of the uh, uh, x equals 1 line, you will see that people who have got higher levels of activity have a higher risk. So physical activity is not universally good. People who have inguinal hernias, osteoarthritis, or carpal tunnel syndrome, for those people who are more active, they appear to have a higher risk of being diagnosed with these conditions in future. However, on the balance of evidence, you can see, for example, for diabetes, urinary tract infections, gallbladder diseases, circulatory diseases, pneumonia, higher levels of activity are certainly associated with a much lower risk. So on balance, physical activity is still an incredibly uh, good thing to be engaged in for people and for prioritization as well. Now, everything I've shown thus far, because at the start I explained we had a triaxial accelerometer that has got 100 hertz in three axes measured, and all I've done thus far is essentially collapse the data down into a glorified average of people who are very active, medium active, not very active, and I'm comparing them against each other. Surely there's much more rich analysis that could be done on that. And one that I'd like to share with you is looking at patterns. So this concept of vigorous, intermittent lifestyle physical activity.
Mhm.
Whew, what do I mean by that? That doesn't roll
Mhm.
off the tip of the tongue. So the idea of this one is that quite often people ask me, or do not ask me, Aiden, how much exercise should I do? Instead, they ask me, Aiden, how little exercise can I get away with? People do not enjoy physical activity so much. So here, what the team in Sydney did was they looked at the right-hand side, a subset of UK biobank
Mhm,
participants who report doing no form of structured exercise.
mhm,
But there are still opportunities for these people to incorporate little bits of activity into their day. Think of you're at the underground station and there's the automated escalator. There's a long queue there. You decide to take the stairs instead. And then maybe three-quarters of the way up, your heart is pounding a little bit because you've actually got in some exercise or vigorous exercise by doing that. Think of the bus about to take off soon, but you're about 100 yards away and you run to the bus. So you get a little burst of vigorous activity to do that. So what the team at Sydney then looked at was how many of these 1 minute bouts or bursts of vigorous activity do people incorporate into their day? And the results are almost miraculous because it shows that people who incorporate three 1 minute bursts of activity into their day apparently have got about a 25 to 30% lower risk of premature mortality than people who do not incorporate any of these bursts. Now, I think, fully believe this because there must be some explanation in the group of people who've got 0 minutes. It might not be because they're so lazy that they choose not to do any vigorous activity. It could be that they have got some other unaccounted for health conditions that means they cannot do some vigorous intermittent lifestyle physical activity. But so tantalizing is this prospect that this paper was published in Nature Medicine a couple of years ago, and its altmetric score was in the top 30 across all of scientific literature published that year. And it certainly merits a further investigation in other cohorts to see if the findings can be replicated. And but then there's much more information that can still be extracted from the device because that was just looking at still quite crude patterns of activity. Instead, for every 30 seconds in a signal, surely there are some time series
mhm,
signal processing methods that can identify patterns or signatures or features
mhm,
that can explain whether a person or classify or identify whether a person is sitting or standing or whether they're walking or whether they're driving or as your group would know whether they're in non-REM sleep or
mhm,
REM sleep or being awake. And in the past, certainly in the physical activity world, there have been some large limitations to approaches taken. The first was trying to develop a ref or a ground truth or reference data set that was realistic. In the past, there was lots of laboratory studies, but not any free living studies. So first of all, what one needs is a ground truth data collection tool. Now, it's much more obvious in the sleep field, whereby there's some obviously very nice polysonography and now at-home PSG kits that one can use. But in the physical activity world, it was not quite so obvious.
mhm,
So what we have been giving to participants over the last 10 years now are wearable cameras. So you could think of them as the police body camera type technologies. They're worn via neck-worn lanyard, take first-person point of view images about once every 20 seconds. In fact, we've now moved towards video. And the from the images, it is bleeding obvious what the person is doing. We know if they're walking, if they're running, if they're having social interaction, if they're eating, if they're sitting, etc., whether they're bike riding in a car. And then what we give the participants in these validation studies is the wrist-worn accelerometer along with that. And the aim then is from the accelerometer to take the or is to try and see if we can identify from accelerometer data alone what corresponds to the label from the image annotation. And up until about 5 years ago, what I would have done for this analysis, working from the bottom of the slide to the top, is I would extract out some raw sensor data. So I might take a 30-second window over the data. I would then extract out and pull out my favorite time and frequency domain features such as the mean of the signal, the median of the signal, the fifth percentile, the 95th percentile, the first Fourier Hertz transform, the eighth Hertz of the Fourier transform, power spectral density, etc. You pick out your favorite time and frequency domain features. You would then run that through something such as a random forest classifier to make a preliminary classification or as to whether the person might be walking or bike riding or sleeping or running. And then we would, because of the time series nature of the data, apply a time smoothing technique such as a hidden Markov model. The intuition of where this is helpful is if for every 30 seconds the classifier thinks I am sleeping, sleeping, bike riding, sleeping, sleeping, it's very unlikely a person went for a 30-second bike ride in the middle of the night, so it smooths over the erroneous classification. But still, we keep wondering about this very first step of the raw sensor data as to what features should I extract. I'm taking out features that I as a human, or statistical features that I as a human understand, but they might not best capture human motion dynamics. So now I'll spend a couple of minutes explaining to you my favorite method in the world.
Actually, this is our favorite as
Oh, oh, good, good.
yeah. Actually, we
Very good.
are actually now adopting it, and actually we are testing whether this idea can be improve our prior work as well.
Oh, brilliant.
Yes, yeah. Please go ahead. But by the way,
I think a
only
very high chance it might,
yeah,
yes.
yeah,
But
yeah.
the so with self-supervised learning, then
Mm,
uh, our a priori, first of all, is that for validation data sets are generally quite small. They're in the hundreds of individuals.
mm-hmm,
So while I would love labeled data, I also realize that there are data sets in hundreds of thousands or millions of people that are unlabeled. And surely there must be something that we can learn from this unlabeled data. Um, so one of the first tasks we've done is using an augmentation self-supervised learning technique. And the intuition here is that in a data set such as the UK Biobank, I don't know what the people are doing, but if I take any 10 seconds of signal, there are some deliberate perturbations I can do to that signal, such as I can flip it around, as in reverse it. I can stretch it out by time warping it, or I can add some permutations to it as well. And then essentially what I can do is I can train a huge neural network and force it to learn features that it needs to extract to then tell if a 10-second segment of data is in its normal form, its reversed form, its permuted form, or its time warped form. And what I can do in a data set such as the UK Biobank is that I can train such a neural network in a data set sorry, I can train that neural network in 7 billion training samples.
mm-hmm,
So I can throw a huge amount of data at it to really learn how to extract the best features. And then essentially, what I can do is if I go to my very right-hand side of my neural network, the first of all, then you can see there are kind of three essentially task heads then. And by extracting these features, it can be incredibly flexible to a number of different tasks. So I could imagine the orange head for one task might be bike riding, the green is cycling, and the purple might be sitting down. But then for another task, I could retrain this to be not sleeping, REM sleep, non-REM sleep states. Or I could instead have it for a person level classification of showing movement characteristics that indicate they have Parkinson's disease versus being in the prodromal state of Parkinson's disease versus being a healthy control. So essentially then what we can do is retrain the final layer of the model, or you can retrain the whole model to uh, um, for a wide variety of tasks, but it's the pre-training in the huge UK Biobank data set that helps us learn some features that are fundamental to human motion dynamics.
mm-hmm.
And now what I've shown is just one possible technique, the one that we use in Oxford, the augmentation recognition. But there are some other techniques out there, such as masking and reconstructing the signal, or also some contrastive learning approaches. And each of these approaches seem very, very promising. At Oxford, our model is trained on the largest data set by far, so we just went with a very simple method, but we are looking at some of the other methods there too. Um, and then how well does self-supervision work? It works remarkably well across different devices, different tasks in different populations. So, for example, if I take the very first line, one is called the Capture 24 dataset. So that's an Oxford dataset. That's a human activity recognition dataset, open, freely available for anyone that would like to use it. And if we train a traditional neural network to identify whether people are walking, bike riding, sleeping, etc., I would have an F1 score of zero point 0.7. However, if I use the pre-trained model in the UK Biobank, to give me a heads up on what features to extract, and then essentially adapt or tweak the model then based on my Capture 24 data, the performance then jumps up by 5%. But then some other data sets, such as the Wisdom data set, it's a laboratory data set of 46 people, F1 score jumps up from 0.68 to zero point 0.8. So it seems to give really large
Mm.
performance improvements, particularly in the smaller data sets where it's more difficult to collect samples. And then, indeed, a set of performance across devices, tasks, and populations, because the MGAFF one is a Parkinson's disease data set. And it even recently I discovered works very well across species. So my favorite paper recently published is from a
Uh-huh.
team in Berkeley who work with a project called the Earth Species Project,
Uh-huh.
where they're doing activity recognition not in humans, but in polar bears and
Oh.
other animals.
Uh-huh.
I'm going to play this video again because I quite enjoy watching it.
Uh-huh.
So with the humans, I said we put cameras on people and the accelerometers. What the team here do is they shoot a dart at the polar bear, then go to it, put a camera on it. As you can see, they also put an accelerometer and gyroscope on the polar bear
Mm.
um, for a validation study, then shoot a dart at the end and collect the data back off it. And what we can what the team then had done is we get down to the bottom left of the screen was their tasks in a polar bear were is its head shaking, is it rolling around, is it grooming itself, is it walking, and by training a neural network on just the polar bear data, the F1 score is 0.23. However, what they then did was took our UK Biobank pre-training model in humans that was trained on obviously a huge sample size, used that to give them a heads up on what type of features to extract, then tweaked and adapted and fine-tuned the model using the small amount of polar bear data they had, and the F1 score goes up from 0.23 to 0.68. And the team in Berkeley didn't stop at that. Then they also used our human pre-training model in rattlesnakes and gulls and whales and turtles and dogs, so across 9 species. And before using the essentially the Oxford self-supervision model trained in human data, the F1 scores were zero point 0.5, but across the 9 species, then the F1 score goes up to almost zero point 0.8. So the self-supervision seems to be really learning some generalizable data that's really helpful across species as well.
So,
Oh, yeah, go
here
ahead,
you
Dave.
use the common self-supervised learning algorithm across all the species, or you have to tuning a little bit across the species?
So it's essentially taking our off-the-shelf uh, uh, pre-trained model in the UK Biobank data,
Yeah,
and
yeah,
then
yeah.
in
Oh, I
yeah,
see.
and then it's fine-tuned in each of those species.
Okay,
So
gotcha, gotcha, gotcha.
So essentially, I know you could imagine a fivefold cross-validation then in the
Uh,
rattlesnake that you would tweak and fine-tune the model then in 4/5 of the data, test in the other fifth, and then just rerun it through
wow.
those. Then when you go to the turtle, then you would be retrain the model then to see whether it's in its feeding state, staying at the surface state, gliding state, or swimming state. And
Wow.
then again, you would adapt for the sea length, see whether it's feeding or traveling.
Mm, makes sense. Wow. Amazing.
Yeah. Yeah, it's really, really cool, that
Yeah.
paper. And then moving back to humans, so how could I use the self-supervision model?
Hmm.
First of all, it's very helpful to identify time spent in different physical activity intensities. So time then spent in light intensity versus moderate intensity. I can do that much more accurately than trained in what I said was the Capture 24 data set. I then deploy it in 100,000 people in the UK Biobank data set. And we could see for cardiovascular disease, physical more time and moderate MVPA, moderate to vigorous physical activity, is hugely and very strongly associated with cardiovascular disease, but not really for cancer. So again, this provides us with new input. Physical activity is very important for cancer, but the intensity of activity do possibly not so important for cancer, very important for cardiovascular disease. I'm going to skip the step count example and instead then show one around sleep measurement. This is a work then by Hang Yuan then that a, a limitation we felt of a lot of sleep work had been a reliance on fairly small data set sizes of wrist-borne accelerometry versus polysomnography.
Oh,
Usually studies were in less than 100 individuals.
uh-huh.
What Hang done then was we collated data using the RAIN study in Australia, a Newcastle study in England, and then also other validation data sets in Pennsylvania in the US and Leicester in the UK. And so in total, we had 1,500 people then with
Mm,
wrist-borne triaxial accelerometry versus
mm,
polysomnography. Using the self-supervision model,
mm,
we used that to pre-train and extract our features, then put it into a recurrent neural network then to identify which of the sleep states an individual is in, wake versus N1 versus N2 versus N3 versus REM. Now, what we found was it was just too difficult from just an accelerometer signal alone to identify whether a person was in N1, N2, or N3 individually. So we put those together then to say whether a person was in REM or non-REM or wake state. And we look at the performance, for example, of the kappa statistic is my favorite one to look at. So if I look at the random forest model, a kappa score of about zero point 0.3, which is seen as maybe poor agreement. But at least then using the self-supervision model, the kappa score goes up to about 0.37, an F1 score of about 0.57. Now, it's an incredibly difficult task, is what we
mm,
found from a movement signal alone. And I imagine what your group is using
mm.
are taking into account physiological signals via PPG sensor, which I think are really, really needed. So I think we've squeezed as much as we can out of the triaxial accelerometer signal alone. But I would think the self-supervision used with the PPG signal in addition to the accelerometer signal would help perform much, much better. The reason we've concentrated on just the accelerometer is because we've got huge data sets of accelerometer only information, such as the UK Biobank and the China Kuduri Biobank. So we really wanted to see could we extract out a good signal from those. Now, the one thing as well to remember, an accuracy score of 62% is not brilliant for wake versus REM versus non-REM, but it's also not rubbish and random. So what we have also done then is combined, or essentially on the 100,000 UK person, biobank person data
Uh-huh.
set, we deployed the model. So then we can see the amount of time people spend nighttime sleep, sleep efficiency,
Uh-huh.
REM sleep, non-REM sleep.
Uh-huh.
And what Laura Portis and our team has done, because we know it's not a perfect signal, but also not a random signal, we've been able to see that, for example, in chromosome 2, as we're looking at all the genetic variants that are associated with differences in REM and non-REM sleep. So what we could see is that in chromosome 2, there's a very large effect
Wow.
for a switching effect essentially between REM and non-REM sleep of about 10 minutes either way.
Uh-huh.
So we're carefully going through that. There's a paper on the Med Archive and
Uh-huh.
it's currently under review as
So,
well of
so
taking the
here, REM sleep,
multiple.
non-REM sleep is based on PSG or your wearable data?
This is based on just the triaxial accelerometer data because
Wow, nice.
unfortunately there's
Okay.
not a large enough data set with PPG
Uh-huh.
and accelerometry data
Yeah.
for overnight sleep assessment. We would love to change that in future, but as
Mm,
of today, there's the only way to do a good genetic study or genome-wide association study is
is
to use the
using the
largest
wearable,
available
right?
data sets,
Yes,
which are
yes,
the
yes.
triaxial
Wow.
accelerometers.
Wow, this is beautiful.
Uh,
Yeah, wow.
and I'm going to skip this one in the interests of time and just discuss for just 2 minutes where are we going next.
Huh?
Uh, so perhaps even one better than PPG is we are collecting ECG information with a cardiac
Mm-hmm.
monitor in 30,000 people. Data collection for that has recently finished. So I'm very hopeful, probably 2027 in the UK Biobank, we will
Mm-hmm.
release the chest wall and cardiac monitoring data. So that's got triaxial accelerometer at 25 hertz plus ECG collected at 250 hertz. The smartphones are exciting. We're considering that in some of our cohorts. Uh, and here's one that was recently published in Israel in 900,000 people who have linked up their smartphone data, in this case step counts, with their electronic healthcare record data. Now, there'll be some challenges with the smartphone whereby it looks like men are much more active than women, but of course, men wear the smartphone in their pockets more, which is a good location to pick up step counts. But
Mm-hmm.
surely there's going to be some signal among this noise. And then one of my very favorite studies in the world right now is in the US, which is the All of Us
Yes.
cohort,
Mm-hmm.
which has given Fitbit data or has Fitbit data collected in 60,000 individuals, 30,000 individuals of whom are linked up to the electronic healthcare record. So what Evelyn and our team then is looking at, along working closely with the All of Us team, is trying to see how Fitbit measurements are associated with future diagnoses of type 2 diabetes, heart failure,
Mm-hmm.
morbid obesity, diastolic heart failure, etc., etc. But what's really neat about the All of Us cohort is that UK Biobank, the median measurement for within a person is about just under 7 days. The All of Us study, the median within person measurement is well over a year. So we're getting much more detailed data on individuals, which is really exciting. And I think this is my second last slide then. Where else do we need to go next? So yes to commercial devices, but really we need information in lower to middle income countries as well. So all of our device-based evidence is from high-income Western settings. We need much more device-based evidence integrated in biobanks in Asia, in Africa, and South America. And I strongly believe that's really a big priority area. And additionally, we need accompanying validation data sets
Mm-hmm.
to reassure ourselves that our algorithms are working well for sleep assessment, activity assessment, etc. So with that, I'm going to finish. And I hope that I've got across to you my excitement for wearables, how I really believe they're transforming the measurement of important health traits. I also hope that I've shown some of the power of self-supervised time series machine learning, which we really believe is foundational to the latest research in this area. And finally, I believe the future is even much, much more exciting than what's happened over the last decade. A huge thank you for your attention and taking time out of your busy schedules today, and I'd be delighted to answer any questions.
Wow.
Thank you.
Wow. Thanks so much, Aiden. Oh, wow. So, yeah. I think, yeah, we are more now motivated to study wearable, definitely. So, everyone, it's a Q&A time. So, please introduce yourself and then ask a question to Aiden. Who want to go first?
Can I defer